mass energy relation, that is E equal to mc square, according to Einstein, mass energy relation, both mass and energy are interconvertible, that is energy can be converted into mass and mass can also be converted back into energy. That's the equation is all about. E is equal to mc square. We can derive that expression using the concept of special theory of relativity, which is developed by Einstein. We will start with the definition of force. Force is defined as the rate of change of momentum, d by dt of momentum, mv. This is according to Newton's second law. And in this particular case, see, generally we will take mass as a constant. According to Newtonian mechanics, mass is a constant. But theory of relativity says that even mass is also variable with respect to velocity. That is, if a particle is moving with a high velocity, then its mass also increases. So in this particular case, we are taking mass also a variable, so that this expression d by dt of mv can be written as m dv by dt plus v dm by dt. That's the expression for the force. Now, when a force is acting on a body, let us say the body undergoes a displacement of dx. During that process, a work is done on the body. Like for example, if dx is the displacement, then f dot dx is equal to the work done dw. Now, when this work is done on the particle, its kinetic energy increases. Let us say increase in kinetic energy is represented by dE. This dE is equal to dW, that is the work done, and it is equal to f dot dx, where f is force and dx is the displacement. We can write what you say in place of force, this entire expression. Therefore, this dE becomes m dv by dt dx, this dx, plus v dm by dt into dx. That's the expression. Further, dx by dt is nothing but velocity, rate of change of displacement is velocity. Similarly, here also dx by dt can be written as velocity v. So from this one, dE can be written as m dv and v, that is mv dv. This dx by dt is replaced by v and dv appears as it is. Similarly, the next term is written as v dx by dt, you will get another v, that becomes v square dm. That is the expression for the increase in the energy of the particle dE. Let us say this to be equation number 1. Next, we'll use a variation of mass with respect to velocity, that is given by theory of relativity. The expression for the relativistic mass is given by this expression, m is equal to m naught divided by under root of 1 minus v square by c square. In this expression, m naught stands for the rest mass of a particle, that is, when the body is at rest, its mass is taken as a rest mass, which is given by m naught. Now, m is relativistic mass in the sense, if the body is moving with a high velocity, then its mass changes, its mass actually increases. Then that relationship is given by this equation. Here, v stands for velocity of the particle and c is the velocity of light. So, from this expression, proceeding further, squaring on both sides of the equation, we'll get m square is equal to m naught square divided by 1 minus v square by c square. We can write this expression as m naught square divided by c square minus v square by c square. Next, that becomes m square equal to m naught square c square divided by c square minus v square. Next, this implies, you can cross multiply this one, that gives you m square c square minus m square v square is equal to m naught square c square. Further, I can write an expression for m square c square, which is equal to m naught square c square plus m square v square. So that is the expression for m square c square. So here we have started with the relativistic mass of a particle, which varies with respect to its velocity, and then we have written an expression by squaring both sides of the equation. Finally we got this expression m square c square is equal to m naught square c square plus m square v square. Now this is the expression which we got. Next we will differentiate this expression on both sides. You can see c square is a constant, therefore this after differentiating you will get c square multiplied by 2m dm, and on the other side m naught is the rest mass of the particle which remains constant, and c is velocity of light, which is also a constant. So when I differentiate this constant, it will give you 0, and then next we need to differentiate this one. That will give you m square differentiation is 2m dm multiplied by v square, plus there is another term, that is m square multiplied by 2v dv. So that is the expression which we got, and here 2m appears on both sides of the equation, so we can divide the whole expression by 2m. So I'll write it here also, divide the equation by 2m. So once you do that one, what you will get here on this side is c square dm is equal to, that will give you v square dm plus mv dv. That is equation number 2. So in this way we got equation 2. You can compare the previous expression, that is equation 1 and equation 2. That is comparing equations 1 and 2. You can see the right hand side of both the equations is the same. In the earlier expression 1, we got mv dv plus v square dm, which is the same as the LHS of equation 2, RHS of equation 2. In such case, we can write this c square dm is equal to dE. So this implies I can write this expression as a change in the energy of the particle dE is equal to c square dm. Now we can integrate this expression both sides. Integration of dE is equal to c square is a constant, integration of dm. That will give you E on this side. Here you have c square multiplied by integration of dm is m. So that will give you E is equal to mc square. That's the final required expression, E equal to mc square. So here what we have done is we have taken the previous expression and then differentiated on both sides. You got this equation, and then we have divided it by 2m. We got this expression, and we have an earlier expression of equation 1. We compared both the equations, and from that we got this one. On integrating both sides of the expression, we got the final expression E is equal to mc square. So this equation tells you that mass is another form of energy. Mass can also be converted into energy. The experimental evidence for this equation comes from pair production and pair annihilation. Like a high energy photon may disappear, and two particles, electron and positron, may be formed. That is, energy of photon is converted into particles having masses. That is one example, and the reverse process may also happen, that mass can be converted into energy. that is observed in pair annihilation, wherein two particles, electron and positron, may combine together and they will result in their energy results in a high energy photon, gamma ray photon. So in this way both energy and mass can be converted from one to other. And this expression is also widely used to calculate the energy released in most of the nuclear reactions such as nuclear fission and nuclear fusion. That is Einstein's mass energy relation.